Welcome to the Deep Dive, your personal shortcut to getting well-informed fast. We've got something truly legendary on our desk today, excerpts from the Feynman Lectures on Physics, the New Millennium Edition.
Right, and it's not just any physics book. For generations of scientists, this is really the foundational text. It captures Richard Feynman's brilliant, sometimes unconventional lectures back at Caltech.
Yeah.
It's really a journey through the fundamental nature of the universe, from the tiniest particles right up to planets moving.
Absolutely. And for this deep dive, our mission, our goal is to navigate this incredible material. We want to pull out the most mind-bending foundational concepts, the kind that genuinely shift how you see the world, all while making sure we don't get too bogged down in the really dense mathematical weeds.
Right.
We're here to give you the core insights, those aha moments, without you needing to tackle all three of those massive volumes yourself.
Exactly. Feynman was just a master at revealing the wonder in physics, and that's really what we're aiming for.
Okay, then, let's unpack this. Let's maybe start where Feynman often does, by imagining the world incredibly magnified. Take, say, a single drop of water and zoom in. Not just a little, but 1 billion times. What would you even see?
Well, at that immense scale, the smooth surface of water, it just disappears. You'd see what look like tiny blobs, black ones for oxygen atoms, white ones for hydrogen atoms.
And they're hooked together, forming those familiar HUO molecules.
Look, they're held together, they attract each other, almost like they're sticky,
Sticky? Yeah.
But if you try to push them too close together, they also strongly repel each other.
What really struck me from the source, though, is that even in these idealized pictures, these little molecules aren't just sitting still.
No, absolutely not.
They're constantly jiggling, bouncing around, twisting, turning.
That's one of the very first profound insights Feynman gives you. This constant dynamic motion is just fundamental to understanding matter. And it's what chemists study when they figure out how atoms arrange themselves in molecules like carbon dioxide, which is a straight, symmetrical structure, OCO.
Yeah, the source even throws in an example of the complex molecules responsible for the odor of violets. It kind of shows how chemists do this incredible detective work mapping these really intricate shapes.
And moving from simple molecules to the really, really complex, the lectures touch on DNA. The source describes it, well, schematically, as two chains linked by pairs.
With very specific pairing rules, right? Like A always links with B and C always with D.
Precisely. And these pairings aren't random. They're based on how the molecules actually fit together and interact energetically.
Okay.
And the mind-bending idea here is that the specific sequence of these pairs along the DNA chains, well, that might contain the actual instructions for building things like proteins.
Wow. Okay, so from that microscopic jiggle, let's zoom way out to the grand scale planetary motion. The source goes back to Kepler's 3 laws describing how the planets move.
Kepler gave us the blueprint, basically. Planets orbit the sun in ellipses, not perfect circles.
Right.
They sweep out equal areas in equal times.
A second law.
Yeah. And their orbital periods, how long they take to go around, relate predictably to their distance from the sun. These were amazing observations, but they didn't explain why the planets followed these paths.
That's where Galileo's principle of inertia comes in, the idea that an object left undisturbed will just keep going forever. Straight line, constant speed.
It's such a fundamental observation about motion. As Feynman puts it, why does it keep on coasting? We do not know, but that is the way it is. It's just a basic fact of how the universe seems to work.
And then Newton, he provides the why, doesn't he, with his law of universal gravitation. This single law connects, the falling apple to the orbiting moon.
Yeah, a classic example Feynman uses is the tides. It's not simply the moon pulling the water directly under it.
It's more complicated than that.
It is. Gravity's pull diminishes with distance. So the water closer to the moon is pulled more strongly than the Earth's solid body, on average. And the water on the far side is pulled less strongly.
Wow.
And because water can flow relative to the solid Earth, this differential pull causes bulges tides on both sides of the Earth.
Right. Right. So to describe motion precisely, Newton needed new math tools. The source talks about concepts like velocity and acceleration.
Exactly. Instead of just average speed over, say, an hour, Feynman focuses on the speed at a single instant. We use the mathematical tool of calculus, the derivative, to capture this instantaneous rate of change.
So velocity is a rate of change of position.
And acceleration is the rate of change of velocity, how quickly the velocity itself is changing.
And motion isn't just in a straight line. It happens in 3 dimensions. So forces in motion, they need direction as well as magnitude, right?
That's why we use vectors. Velocity is a vector, because if you tilt your perspective, its components like how fast you're moving left-right versus up-down change in a specific, predictable way. Force is also a vector.
Which leads us to Newton's famous FMA. It almost sounds like just a definition. If something's accelerating, well, there must be a force.
It kind of does, yeah.
But Feynman explains it's much more than that. It's a fundamental law. It comes from observing how forces add up and how they relate to momentum in actual experiments. Okay. Now, beyond gravity, the source briefly mentions other fundamental forces.
Yeah, primarily the nuclear forces, the ones holding the nucleus of an atom together.
Strong and weak nuclear forces.
Right. And the fascinating points here are that, 1, we don't have simple formula for them like gravity yet. 2, their reach is incredibly tiny, only about 10 even centimeters.
Minuscule.
And crucially, you can't describe them accurately using Newton's laws. You need quantum mechanics for that scale.
So they're super strong within that tiny range, but essentially vanish outside of it.
Exactly. They have a very, very short fuse, you could say.
Now, here's where it gets really interesting, maybe a little counterintuitive. This idea of pseudo-forces.
Ah, yes. Yeah. These forces, they feel totally real to you, but they aren't fundamental pushes or pulls like gravity or electromagnetism. They sort of pop up when your frame of reference is accelerating.
Like in a car.
Exactly. Imagine you're in a car accelerating forward. You feel a force pushing you back into your seat. That's a pseudo-force. It only exists because you are accelerating relative to the ground.
Okay, I get that. And the provocative question Feynman raises then is, could gravity itself actually be a pseudo-force?
He illustrates this with that famous thought experiment.
Yeah.
A person in a closed box.
Right.
If the box is just sitting on Earth, they feel gravity pulling them down, proportional to their mass. Okay. Now, take the box out into empty space, far from any planets or stars, but accelerate the box upwards at exactly 9.8 meters per second squared, the same as Earth's gravity. The person inside will feel a force pushing them down onto the floor, also proportional to their mass. To them, inside the box, it feels identical to gravity.
Wow. You wouldn't know the difference.
You wouldn't. And this equivalence is actually a cornerstone of Einstein's general relativity.
Amazing. Okay. Moving on to one of the most fundamental concepts in all of physics, energy and work. How does Feynman define work done by a force?
Well, work is done when a force actually moves something. Specifically, it's the force applied multiplied by the distance moved in the direction of the force. That last part's important.
So if you push sideways on something moving forward, you're not actually doing work on its forward motion.
Exactly. No work in terms of changing its forward kinetic energy.
And this work changes the kinetic energy, the energy of motion.
Precisely. Do work on an object, you change its speed, its kinetic energy. Then there's potential energy, like gravitational potential energy, which depends on position. The source points out a really remarkable fact about gravity. The potential energy outside a uniform spherical shell of mass is exactly the same as if all that mass were squished down to a point at the center.
That sounds useful for calculations.
Oh, it's incredibly useful. It's a mathematical trick that simplifies things immensely.
And the big headline from this whole section is the conservation of energy.
Yeah. In a closed, isolated system, the total energy that's kinetic plus potential remains constant. Energy isn't created or destroyed, it just gets transformed from one form to another.
But hang on, what about things that seem to lose energy, like a ball rolling to a stop? Where does its kinetic energy go?
Ah, good question. That's where Feynman clarifies that internal energy is part of the total energy picture.
Yeah.
The ball stops because of friction.
Right.
And friction is basically molecules bumping and jiggling against each other more vigorously. That's heat. Thermal energy.
So the energy is still there, just microscopic.
Exactly. Or think about gasoline burning in an engine. Stored chemical potential energy is released as heat and the kinetic energy of expanding gases. Even though the gasoline disappears, the total energy is conserved, just converted into that microscopic jiggling and macroscopic motion.
This idea of different forms of energy all being part of one conserved total is crucial, which I guess brings us back to relativity. The source mentions Galilean relativity first.
Right, the old idea that mechanical laws were the same for anyone moving at a constant speed. But this didn't seem to work for light and electromagnetism.
Why not?
Because Maxwell's equations predicted light always travels at the same speed. See? But intuitively, if you were moving towards a light beam, shouldn't you measure its speed as faster or slower if moving away?
Yeah, that makes sense.
This contradiction led physicists down a bit of a rabbit hole, including this idea of a light-carrying ether filling space.
Which the famous Michelson-Morley experiment in 1887 tried to detect and found nothing.
Exactly, a really perplexing null result, which led to ideas like the Lorentz contraction that maybe things physically shrink when they move, just enough to hide the ether's effect.
That sounds like a fudge factor.
It kind of did, but it led to the Lorentz transformation equations, which correctly describe how space and time coordinates actually change between moving frames of reference.
And hidden in those equations was a term that just completely shattered our everyday intuition about time.
That surprising X-caught term in the time transformation equation. It means that events that happen simultaneously for someone standing still, well, they do not happen simultaneously for someone speeding by. Time itself is relative. It depends on your motion.
Mind blown. Still is, every time I think about it. And from these ideas, of course, comes the most famous equation in the world.
E-men-c-c-c-o-g-s. Mass and energy are equivalent. They're two sides of the same coin, and they can be converted into one another.
The source gives some powerful
Oh
example.
yeah, an atomic bomb releasing enormous energy by converting just a tiny amount of mass, maybe a gram or so, for a huge explosion. Or even more fundamentally, the complete conversion of mass to energy when an electron meets its antimatter counterpart, a positron. They annihilate each other,
Right.
leaving only energy, like gamma rays.
Feynman revisits a philosophical point here, too, about what concepts are even allowed in physics.
Right. Classical physics kind of assumed things like exact position or exact momentum existed, even if we couldn't measure them perfectly. But relativity, and especially quantum mechanics, show that some of these classical concepts aren't useful, maybe not even meaningful, at certain scales.
So it's not about whether you can measure it perfectly.
Not entirely. Feynman argues science doesn't have to demand that every concept is directly measurable, only that the overall theory is useful and predicts experimental results correctly. It's less about what must exist in some absolute sense and more about what works to describe reality as we observe it.
That makes sense. And unifying energy and momentum even further, the source mentions they form a four-vector in relativity.
Yeah, they kind of blend together into a single entity in four-dimensional space-time. Very elegant.
Okay, let's shift gears entirely now to waves and light. Feynman makes a really key point early on that in quantum mechanics, the distinction between waves and particles, well, it kind of breaks down.
It really does. Everything in the universe, fundamentally, has both wave-like and particle-like properties. It's called wave-particle duality.
So which aspect do you see?
Well, you tend to see the wave side more clearly with things like light at low frequencies, like radio waves, and you see the particle side more at high frequencies, like gamma rays, or we're looking at individual things like electrons hitting a screen. But it's all part of one unified picture.
And when waves combine, they interfere. This leads to all sorts of fascinating effects.
Oh yeah, like beats, if you have two sound waves with slightly different frequencies, you hear that wah-wah-wah sound.
Uh-huh.
Or you get complex patterns when adding multiple waves together. The source introduces concepts like wavelength, frequency, and wave number to describe these waves mathematically.
What's particularly relevant for quantum mechanics, though, is the idea of confined waves.
Right. Imagine waves on a string fixed at both ends, like a guitar string. Only certain wavelengths and frequencies are possible. The string can only vibrate in specific patterns or modes. It can't just vibrate at any old frequency.
And this is directly analogous to how atoms work in quantum mechanics, isn't it?
Exactly. The electron waves, confined within the electric field of the atom's nucleus, can only exist in specific modes, and these modes correspond to the atom having definite, discrete energy levels.
So atoms can't just have any energy.
No. An atom typically exists as a combination, a superposition, of these definite energy states. It's the wave nature of matter that explains why atoms have these fixed energy levels, which is fundamental to chemistry.
Interference isn't just abstract math either. We see it all the time.
Absolutely. Think about the shimmering colors in soap bubbles or oil slicks on wet pavement. That's light waves, reflecting off the front surface and the back surface of that thin film. These reflected waves interfere, sometimes canceling out certain colors, sometimes reinforcing others, depending on the film's thickness and the angle you're looking from.
The source also explains why light slows down when it goes into materials like glass or water. That gives us the concept of refractive index.
Yeah, Feynman uses a simple but quite effective model. The incoming light wave makes the electrons in the material oscillate, like little driven springs.
Okay.
These oscillating electrons then re-radiate light waves of their own, which combine or interfere with the original light wave. The net result of all this interaction is a wave that appears to travel slower through the material. That effective speed change is measured by n.
And this interaction also explains why different colors bend at different angles when they go through a prism, what's called dispersion.
Exactly.
Okay.
Because the way the electrons in the material respond depends on the frequency, the color, of the light hitting them. So the refractive index changes slightly for different colors. Red light bends a bit differently than blue light, causing them to separate out.
Makes sense. And if the material can absorb energy from the light wave, maybe converting it to heat, the source shows how that gets handled mathematically.
Yeah, the math gets a bit more involved using complex numbers for the refractive index, but the physical intuition is that energy is being transferred from the light wave into the material's internal energy. It's jiggling atoms.
Speaking of radiating energy, oscillating charges radiate energy. That's fundamental.
It is. It's fundamental electromagnetism. And it's why antenna work, you oscillate charges back and forth in the antenna wire to radiate radio waves out into space.
And that energy has to come from somewhere.
Right. The energy radiated away shows up back in the antenna circuit as a kind of resistance called radiation resistance. It's like a resistor that doesn't get hot, but instead converts electrical energy into waves that fly off into the cosmos.
The source also touches on polarized light. What's that about?
Okay, so light waves are transverse waves, meaning they oscillate perpendicular to the direction they're traveling. Normally, the oscillations happen in all directions perpendicular to the path.
Okay.
Linear polarization means the oscillation is confined to just a single plane. Imagine whittling a rope up and down versus side to side.
Right.
Materials, like polarizing filters, like in good sunglasses, are designed to absorb light polarized in one direction while letting light polarized perpendicular to that direction pass through. It's incredibly useful technology for reducing glare, 3D movies, all sorts of things.
And finally, the Doppler effect for light. Similar to sound.
Very similar in principle.
Yeah.
Just like a train whistle sounds higher pitched, higher frequency when it's coming towards you, and lower pitched when it's moving away.
Yeah.
The frequency, which for light means the color, shifts if the light source is moving relative to you. Light from something moving towards us gets shifted to higher frequencies, towards the blue end of the spectrum blue shift. Light from something moving away gets shifted to lower frequencies, towards the red end red shift.
And that's how astronomers measure cosmic motion.
Exactly. It's how we know distant galaxies are moving away from us, and how fast. It's a vital tool in cosmology.
Okay, now let's take all that physics of light and connect it to the physics of seeing. The source actually dives into the sensation of vision itself.
It does, and it makes a really critical distinction. It separates the physical properties of light, like the exact mix of wavelengths hitting your eye, from the subjective experience of color that happens in your brain.
Because different combinations of wavelengths can actually look like the same color to us, right?
Precisely. Our eyes and brain don't analyze the full spectrum perfectly. The chromaticity diagram is a tool Feynman introduces to show how colors relate mathematically, almost like vectors.
Vectors for color.
Yeah. Mixing colors is like adding these vectors on the diagram, and it shows why mixing just 3 well-chosen primary colors of light can effectively fool our brains into perceiving almost the entire range of colors we can see.
And seeing isn't just about detecting light and color. The source really emphasizes the brain's role in interpretation.
Hugely important. We don't just see disconnected patches of light and color. Our brain actively interprets them, constructing objects, faces, scenes, recognizing patterns. It's a very active process.
The source also points out some surprising, maybe even weird biological details about the eye's structure.
Yeah, like the fact that the light-sensitive cells in the retina, the rods and cones, are actually behind other layers of neurons and blood vessels that the light has to pass through first. From an engineering perspective, it seems kind of inside out.
That is strange, and the neural wiring from the eye back to the brain is fascinating too.
It is. The optic nerve carries signals from the retina to a crossover point called the optic chiasma.
Yeah.
Here, fibers from the right side of both retinas get routed to the right hemisphere of the brain, which means the right side of your brain is processing the left half of your visual field, and vice versa, for the left brain and right visual field.
That crossover sounds important.
It's absolutely essential for our binocular vision, for combining the slightly different views from each eye to judge depth and distance accurately.
All right. Shifting scales again, let's go from individual eyes to the behavior of matter in bulk, the realm of thermodynamics and kinetic theory. The source needs this is maybe a trickier subject than mechanics or light.
It can be, yeah, because you're dealing with the collective behavior of just unimaginably vast numbers of particles, atoms, and molecules. The kinetic theory is where you try to understand macroscopic properties, like pressure or temperature, by thinking about the microscopic action.
Like gas pressure, for instance. You mentioned that earlier.
Right, that pressure you feel from the air or inside a balloon isn't some mysterious force field.
Yeah.
It's simply the cumulative effect of countless air molecules constantly bouncing off the surfaces, billions upon billions of tiny impacts per second.
So if you squeeze a gas into a smaller volume.
The molecules are closer together, they hit the walls more often, so the pressure goes up. If you add energy, heat them up, they move faster, hit the walls harder and more often, so again the pressure goes up. It connects the micro and macro.
This microscopic picture leads to some really powerful general principles, doesn't it?
Oh, absolutely, like the equipartition theorem. It's a profound idea. It states that in a system in thermal equilibrium, meaning everything's settled down at a stable temperature, the total internal energy is distributed, on average, evenly among all the independent ways the particles can move or store energy.
We call those degrees of freedom.
Exactly. So for a simple atom just bouncing around in 3D space, it has 3 degrees of freedom for motion, left, right, up, down, forward, back. On average, each of those directions gets the same amount of kinetic energy, and that amount is proportional to the absolute temperature.
What about molecules made of multiple atoms?
Well, they have more degrees of freedom. They can still move around, translation, but they can also rotate, and the atoms can vibrate relative to each other. Each of these possible motions counts as a degree of freedom and gets its share of the energy, on average.
So that explains why temperature relates to the total internal energy?
Precisely. And this also leads to understanding things like the distribution of molecular velocities, the famous Maxwell-Boltzmann distribution, which tells you how many molecules are moving at what specific speeds at a given temperature. Not all molecules move at the same speed.
The source also links evaporation of a liquid to this kinetic picture, right? How does that work?
Yeah, it's a nice application. Think of the molecules in a liquid. They're attracted to each other, held together, but they're still jiggling around with a range of kinetic energies.
Okay.
Occasionally, a molecule near the surface happens to get enough kinetic energy from collisions to overcome the attractive forces holding it in the liquid. If it's heading outwards, poof, it escapes into the vapor phase. That's evaporation.
And since only the high-energy ones escape,
The average energy of the molecules left behind goes down. That's why evaporation cools the remaining liquid. It takes energy to evaporate.
and collisions between molecules are essential for all this, for reaching equilibrium.
Absolutely crucial. Molecules are constantly bumping into each other, exchanging energy. This shuffling process is what allows the system to reach thermal equilibrium, where the energy is distributed according to that equipartition principle. The average time between collisions, often denoted by tau, is a really important parameter for understanding how quickly things like momentum or heat can spread through a gas or liquid diffusion, viscosity, thermal conductivity, all depend on it.
Then the source transitions to formal thermodynamics, which deals with energy, heat, and work on a macroscopic level, often without touching all those microscopic details.
Right. Thermodynamics rests on a few very general fundamental laws discovered through experiment. A key concept is the efficiency of engines' devices that convert heat energy into useful mechanical work. The source introduces the idea of reversible engines and Carnot's postulate. Sadi Carnot figured out way back that no engine operating between two specific temperatures can possibly be more efficient than an ideal, perfectly reversible engine operating between those same two temperatures. There's a theoretical maximum efficiency.
And Feynman uses a clever argument to show why this must be true, right? Involving running engines backwards.
Yeah, it's a classic thermodynamics argument. If you could build a super efficient engine, you could use its work output to run a standard reversible engine backwards, making it act like a refrigerator. The net effect, if you do the accounting carefully, would be transferring heat from a cold place to a hot place with no other change, or maybe even extracting heat from a single reservoir and turning it purely into work. And that we know from experience, and the second law of thermodynamics, is impossible.
So that impossibility proves Carnot's postulate.
Exactly. And this whole line of reasoning leads directly to the definition of a very important quantity called entropy, usually labeled S.
Entropy. That always sounds mysterious.
It can seem that way. But fundamentally, entropy is a state function, meaning it's a property of the system itself, like its pressure or temperature, at a given moment, regardless of how it got into that state. For reversible processes, the change in entropy is defined as the amount of heat added divided by the absolute temperature at which it was added. It turns out to be a measure of the disorder, or the randomness, or the dispersal of energy within the system.
The source gives an example of a Carnot cycle using a material that can easily change phase, like water turning into steam.
Yeah, that's a practical example. It highlights a crucial point on a pressure volume diagram, where you can add heat to the substance, like boiling water, but its temperature doesn't change. Instead, the energy goes into changing the phase from liquid to gas. This isothermal expansion is a key part of the Carnot cycle in many real-world heat engines.
Now, woven throughout all these specific physics concepts, Feynman includes these wonderful reflections on the nature of science itself, the process of discovery, and even the challenges of learning and teaching.
Oh, definitely. The History of Errata section mentioned in the notes is a great example. The lectures were originally transcribed and published quite rapidly from recordings,
Yeah.
and inevitably, errors crept in. Many of these were found and pointed out later, often by students and readers around the world who were carefully working through the material.
That's actually quite wonderful, isn't it? It's a very humble reminder that science isn't delivered like commandments on stone tablets. It's built piece by piece and corrected iteratively by a whole community.
Exactly. Even brilliant minds like Feynman make mistakes or things get transcribed incorrectly. And finding and fixing those errors is a vital part of how knowledge actually moves forward. It's self-correcting.
Feynman is also apparently quite candid, maybe even a bit melancholic, when reflecting on how effective the lectures actually were for the Caltech students he was teaching at the time.
Yeah, he quotes the historian Edward Gibbon something like, "The power of instruction is seldom of much efficacy except in those happy dispositions where it is almost superfluous."
Ouch. That's a bit pessimistic about teaching.
It kind of is. It suggests that while good teaching certainly helps, truly deep understanding often requires a certain innate spark or curiosity or maybe just the right kind of prior preparation from the learner themselves. It's not just about pouring knowledge in.
He also reiterates the idea we mentioned earlier that physics is really the foundational natural philosophy underpinning chemistry, biology, geology, engineering.
Right. Understanding the fundamental physical laws gives you the basis for understanding how everything else works, at least in principle, although the complexity quickly becomes overwhelming in practice for things like biology.
And he returns to some of those philosophical ideas we touched on about what concepts are valid in a scientific theory. Like, do they absolutely have to be directly measurable?
Yeah, he contrasts the classical view, which kind of assumed that things like the exact position and exact momentum of a particle existed simultaneously, even if we couldn't measure both perfectly, with the quantum mechanical view.
Where Heisenberg's uncertainty principle says you can't know both exactly, even in principle.
Right. And Feynman aligns with Heisenberg's pragmatic point. You don't have to be able to answer questions that you can't even experimentally ask. If a concept like the exact path of an electron in an atom isn't measurable and isn't needed for the theory to work and make correct predictions, then maybe demanding it exist is unnecessary. Science evolves which concepts are useful and consistent with observation.
He also points out that some concepts we use, like the direction given by the right-hand rule for calculating cross products or magnetic forces, are based on human convention.
Exactly. These are sometimes called pseudo-vectors or axial vectors. Their direction depends on an arbitrary choice, like which way is right, unlike true or polar vectors like force or velocity that seem to have an inherent direction in space independent of our conventions.
And finally, there's that striking observation that connects fundamental physics to biology, chirality, the whole idea of mirror image molecules.
Yeah, handedness. Molecules can exist in left-handed and right-handed versions, like your hands. They're mirror images, but can't be superimposed. Chemically, they often behave identically in simple reactions.
But life is different.
Astonishingly different. Life, as we know it, almost exclusively uses only one version for building crucial molecules like proteins, the L-amino acids, the left-handed versions. The D-amino acids, the right-handed ones, exist. Chemists can make them easily.
So if you synthesize amino acids in a lab from simple starting chemicals,
You get pretty much a 50-50 mix of the L and D forms. But life overwhelmingly picks L for proteins and D for sugars. That is a huge, fascinating question. This stark preference in biology, while non-biological chemistry produces both equally, raises a really fundamental question. Are the underlying laws of physics themselves perfectly symmetrical when reflected in a mirror? Or is there some subtle, perhaps fundamental asymmetry in nature, maybe in the weak nuclear force, that somehow nudged early life down this one-sided path billions of years ago. It's still debated.
So there you have it, a pretty deep dive into just a fraction of Richard Feynman's insights. We've explored everything from the dynamic jiggle of atoms and the conservation of energy.
To the relativity of time, the wave nature of light and matter, and even the surprising physics behind how we see color.
It's incredible, really, to see how interconnected all these ideas are, how understanding the jiggling of atoms gives us kinetic theory and thermodynamics.
How wave interference explains the colors you see in a soap bubble and the discrete energy levels inside atoms.
Or how a simple thought experiment about someone in an accelerating box leads to profound questions about the very nature of gravity itself.
Absolutely. And the journey through Feynman's physics isn't just about learning the facts or the formulas. It's about appreciating the process, questioning intuition, understanding the crucial role of experiment, realizing science is this ongoing human endeavor constantly being built, refined, sometimes finding errors like those errata along the way.
Yeah, those specific details, like the errata or the strange inside-out structure of the retina, they really make the story of physics come alive. It's not just abstract laws, it's about exploration and discovery.
Definitely.
So for you, the listener, hopefully the next time you see steam rising from a hot drink or notice the vibrant colors in a hummingbird's feather or even just feel that familiar everyday pull of gravity, well, maybe you now have a slightly deeper connection to the fundamental principles at play thanks to this dive into Feynman's perspective.
It's a powerful reminder, isn't it?
Yeah.
That the world around us is just infused with fascinating physics, often hiding in plain sight, just waiting to be understood if you know how to look.
And here's a final thought for you to mull over, building on that intriguing point about chirality we just discussed. If many of our fundamental physical theories suggest the laws of nature should be perfectly mirror symmetrical, what does it imply about the universe, or maybe about the origin of life, that life itself, at its most basic molecular level, exhibits such a profound and stark preference for just one mirror image? Something to keep exploring.